So, now we sort of look into our last topic related to the fundamentals of surface tension. Is one of the consequences of this surface energy and interfacial energy on a liquid meniscus, and that is Laplace pressure. What we know from our basic fluid mechanics knowledge is that fluid surface which is stagnant and is at mechanical equilibrium, the pressure on the two sides of the surface is equal. That is, if you have a liquid surface, this is, let us say, it is exposed to air, and you have liquid here, and this is atmospheric pressure, let us say. So, what we know so far, that the pressure at the interface, both at the air side and at the liquid side, are same, and they are P atmosphere. So, if one is looking at a tank, open tank for example, pressure at any depth h is plus rho g h. So, one says that within the tank the pressure distribution is hydrostatic, purely hydrostatic. Now, this we know, but what is implicit in this knowledge is that the liquid air interface is perfectly flat. This is the implicit assumption that goes in. However, what turns out, and we will soon realize, that when it is not, this is not valid if the interface is not flat. And if the interface has a curvature, in fact the pressure distribution. So, if this is the interface, this is liquid and this is, let us say, air, just the way we drew the drop for example, while considering Young's equation, well, the liquid is in fact exposed to atmospheric pressure. However, we will soon see that though the pressure on the air side is P atmosphere, it is not same on the liquid side. In fact it is different. So, there is a pressure discontinuity, and this discontinuity is in fact attributed to surface tension. Just because you can also correlate it, like after all this curved shape of the meniscus is also due to surface tension, is a surface energy minimization that is responsible. This phenomena was in fact discovered more than 200 years back by Young and Laplace, and therefore, this pressure difference is called the Laplace pressure, and the equation that governs Laplace pressure is called the Young-Laplace equation. So, let us consider a very simple example. We have a liquid bubble with let us say radius r. So, this is liquid and this is air on this side. Let us say that the pressure inside the drop is P double dash and outside is P dash. Now, let us consider that the radius, initial radius of the bubble, which is r, sort of expands from r to r plus dr, right. So, we know from our basic concept of thermodynamics that the so this is in fact wrong, it is P dV. So, we know that the pressure required, the work done to achieve this is essentially the delta P, that is actually the pressure, the net pressure, that is P double dash minus P dash into dV, right. So, it is delta P into dV, right. We typically consider okay, I will not talk about it, I will talk about something, I will just highlight something later. We have a tendency of when we draw a piston about considering it to be P dV, we consider it to be P because we simply assume that the other side it is open to atmospheric pressure, and therefore, it is considered to be 1. So, if we consider the gauge pressure, it is only P. So, we know that again this is wrong, unfortunately, it is dV. V is 4/3 pi r cube for a sphere, therefore, dV is 4 pi r square. When I upload this PPT in the online material, I will correct this. This is a mistake. This is going to be dV, and the expression for dV, it is not dA. Therefore, the work done is, you can see, it is delta P times 4, this is dr will come here, delta P times 4 pi r square dr. This is the expression of W. I will just neatly write it down here. So, work done is P double dash minus P dash into dV. V is 4/3 pi r cube. Therefore, dV is 4 pi r square dr, and therefore, the expression of W is delta P into 4 pi r square dr. Now, what you need to understand is that as the radius of the drop increases from r to r plus dr, and you need to do work for that, mechanical work of course. Not only does it lead to increase in the volume, but it also leads to increase in the surface area. What is the, so as the surface area changes, so the, let us say the surface area changes by an amount delta A. So, it also leads to a change in the total surface energy, or the total energy that is ascribed at the surface. So, let us say ES is the initial surface energy, it is gamma into A, and upon expansion the DES, where the energy or the work you have done is essentially manifested, is gamma into dA. Now, we know for a perfect sphere A is 4 pi r square, therefore, dA is going to be 8 pi r dr. Therefore, what we get is the work that you have done has essentially led to increase in the surface energy of the drop. So, we equate dEs as equal to the W, what you have got, and what we get is 8 pi r dr into gamma is equal to delta P into 4 pi r square dr, or one gets delta P is 2 by r into gamma. So, you can see for a spherical drop, the delta P across the interface is 2 by r into gamma. What is more important, it is related to the radius of the drop and the surface energy, right. So, this is important, and this P is what is called as the Laplace pressure. But it is important to note that a spherical drop is a special case of an arbitrarily curved surface, because in 3D space any curvature can be represented by the two orthogonal curvatures R1 and R2, or two orthogonal radius of curvature R1 and R2, and a spherical surface is a special case where the two orthogonal radii of curvature R1 is equal to R2, it is the spherical drop. So, let us look into a more general situation. Let us consider a non-spherical curved surface like this. Where the two radii are, let us say, R1. Now, there are some assumptions in this, but it is perfectly fine, and we will see. Let us say the length, this length is x, this is y, the angle subtend is theta here and alpha here. So, these are the two orthogonal radii of curvature. So, if you just provide the so just the way in 3D space you need 3 coordinate to be defined to identify a specific point in whatever coordinate system you choose, like similarly you essentially need to define simply the 2 radii of curvature to generate a curved surface or a section of the curved surface. So, if you want to, so what we do is that we consider a curved object, pretty similar consideration as the previous case. The pressure inside is P double dash, pressure outside is P dash. Instead of assuming it to be spherical, we now consider that it has 2 radii of curvature R1 and R2, and we are simply looking at a small section of it, of this thing. So, this the length is x, this is y. So, we sort of look into the 2 projection views. So, this is along one of the radius, the view taken along one of the radius is R1, and from the other side it is R2. Now, the same thing, you do some mechanical work and this drop, non-spherical but curved drop, sort of expands, and as a consequence of expansion the radius R1 expands by an amount delta z, the radius R2 also expands by an amount delta z. So, this was the original location of the surface, and this is upon expansion this is how the configuration takes like. So, this was R2, this is delta z, this was R1 and this is delta z. So, there is only one assumption, and which is very logical, that the expansion along both the radii is same. So, it is a sort of an isotropic material, which is a very common assumption to make. So, as a consequence of this expansion, the change in the area, surface area dA, one can find as x plus dx into y plus dy minus xy. So, again there is a small assumption that we are looking at very small values of theta and alpha, and for those small values x and y can be considered to be linear. Therefore, the area of this segment we are considering can be simply considered to be x y, and then it expands to x plus delta x and y plus delta y, and therefore, the increased area is x plus dx into y plus dy. So, if you expand, this will turn out to be this, neglecting the term containing dx and dy, assuming it to be very small, and the term x y gets cancelled out. Therefore, the change in the surface energy is gamma times, and the work done is delta p into dv, and which is in fact delta p into xy dz. That is the change in the volume that has taken place. This is the volume by which it has expanded, right. So, we can equate them, but before we do that, we just do a very small bit of geometric maneuver. So, let us look into these individual segments. We have already assumed that for very small values of theta, this segment is linear. So, if we consider that, this in fact turns out to be 2 similar triangles. And what we get is, from the properties of similar triangle, the x plus dx by x is equal to r1 plus dz divided by r1, and from here what we get is dx is equal to x by r1 into dz. Similarly, considering from the other side, we will get y plus dy divided by y equal to r2 plus dz divided by r2, and this gives us dy to y plus y by r2 into dz. So, now simply equating these two, so what we get is we get des equal to gamma. We simply replace dy with this expression what we have got here, x into y by r2 dz, and here again we replace dx with the expression we got from here. So, xy into dz by r1, and this, as we have already argued, equates with delta p into xy into dz. So, here also on the right hand side you find gamma into xy dz comes out as common, and you are left with 1 by r1 plus 1 by r2. You can write 1 by r2 plus r1, does not matter. So, these terms cancels out, and what you get is a very neat equation which is known as Young-Laplace equation. So, you now see that there is some pressure difference across a liquid meniscus because of the effect of surface tension, and for an arbitrarily curved surface with at any given point the two orthogonal radius, if the two orthogonal radius and r1 and r2, Young-Laplace equation in fact correlates the delta p with the surface tension and the local radius of curvature. This is a very, very useful equation. In fact, it can be used in many cases. It is important. I will just talk about a few examples very quickly. One quick example, we will use it later, but the take home very important message is that the moment there is a curvature over on a liquid surface, in fact there is a additional pressure effects that come in, and these effects are attributed to surface tension. So, that sort of brings us to the end of our initial discussion on surface tension. We can just take couple of minutes to sort of find out what are the things we have learned in this particular text. We started to understand the importance about surface tension, or understand what is surface tension, and primarily we understood that surface tension is the energy that you need to spend to create some surface per unit area. So, typically surface tension is energy per unit area, and it is the amount of energy that you need to spend to create unit area of a particular material surface. Why do you need to spend the energy? You need to spend the energy essentially to, so suppose this is a bulk and you have these molecules, there is some interaction between these molecules. Of course, omnipresent or always present is van der Waals interaction. Now, if you would like to, there can be other type of interaction like polar interaction. So, van der Waals is always present, and then depending on the material, nature of the material, you can have polar interaction, you can have steric interaction, etc. So, these are individual molecules, they are all interacting with each other. Within the bulk, the coordination number of all the molecules are roughly the same. So, the net interaction force acting on a molecule is almost 0. Now, you want to create a surface here. So, what you actually have to do is you have to supply adequate energy so that you can overcome the interaction of all the molecules along which you would like to create the surface. So, this is the energy that you need to actually spend to create your surface, which is fine, but once the surface has been created, then additionally what you see that the surface molecules are in an under coordinated state as compared to the bulk molecules. So, the net interaction on a surface molecule is no longer 0. It is always subjected to a net inward interaction due to the presence of the molecules on one side, but there is no net interaction on the other side. So, this is manifested, this can be the other way of looking into what is surface tension, and also the word tension, because as if the surface molecules are sort of pulled inward by the molecules of the bulk. Very important thing to note, surface tension has to be positive. We have already understood, and we now also understood what is the difference between gamma I and gamma ij. Gamma I typically is surface tension. Of course, it is an interface, but it is the interface of a condensed phase with a non-condensed phase. Gamma ij is the interfacial tension. It is the interface of one condensed phase with another condensed phase, right? And we subsequently started to look a more detailed molecular level picture of surface tension and interfacial tension, and then we realized that interfacial tension in fact can be negative. This is a very interesting observation, and we also realize that this is responsible for colloidal stability, and we started to look into the various components of surface tension and interfacial tension, and then we came up with an understanding that gamma ij Lw, the interfacial tension due to van der Waals interaction, is always positive. In fact, this implies that in both the cases, adhesion between 1 and 2 dissimilar surfaces or dissimilar surfaces in air, or adhesion between two similar surfaces in a liquid 3 for a polar material is always going to happen. So, you cannot have a stable colloid of apolar particles in an apolar liquid, and what is going to cause the problem is the van der Waals component of interfacial tension. You can have, if you have polar interaction in your system, depending on the relative strength of the individual components, that is the first to say is the relative magnitude of the cohesive and the adhesive components of the polar components of the individual component, components, you can have a positive or negative value of interfacial tension. In order to mathematically represent the polar components of interfacial tension, we sort of introduced two semi empirical parameters, gamma minus and gamma plus, which represents or talks about the acid giving, the electron giving and electron accepting conjugate parameters. We have discussed it in great detail. We also had come up with a some sort of a relation, it is a geometric mean, to represent the polar component of an individual, polar component of surface tension of an individual material through this relation, and we also had come up with a relation that talks about the free energy change when two objects both having polarity come in contact with each other, and the relation that we wrote is something like this, where you in fact notice that these are the two adhesive components, these are the two cohesive components of the polar interaction within a material, and this is the polar interaction or the cohesive component of polar interaction between the two materials 1 and 2, and depending on the relative magnitude of these two, it may be possible that delta G 1 to AB might be positive, and which is necessary to have colloidal stability. One more interesting example I would like to give. So, these are the things we have sort of done in the last few lectures, and I would request you to go through them some sort of again, and then I think this recapitulation that what we are doing would really help. The last thing that we came up is surface tension also manifests or leads to a pressure discontinuity or some sort of an additional pressure difference even across a liquid surface which is at mechanical equilibrium. However, if it is not flat, if it has a curvature, there exists a difference in pressure between the inside and outside, and this delta P is related to surface tension by the young-laplace equation. And you can also now understand, this is something that we will use significantly later, that if you have a curvature like this, since the R1 in this case is positive and this case is negative, the nature of delta P, so let us assume this is exposed to atmosphere, the nature of delta P is going to vary from this point to this point. So, here delta P is going to be positive and here delta P is going to be negative. What it means that outside pressure remaining constant in both the cases, the pressure inside pressure at this point is going to be higher than the inside pressure here. We always know that if there is a pressure difference, it triggers flow. So, you can expect an undulating surface like this to have some stabilizing flow from this point to this point, and the level should flatten down, which is of course valid because a flat level for a film or a liquid represents a lower surface area configuration. I think this I will take up in greater detail, this particular concept I will take up in greater detail when I discuss thin film instability, but this flow is triggered by the difference in the Laplace pressure at the 2 points. So, I stop here this particular lecture. We are pretty much done with what I wanted to discuss on surface tension, the basic concepts, and from the next class we will move on to the second aspect that we had discussed in the content part, and that is the patterning part, and we get started with photolithography. Thank you.